So where we were, I mean, what we've been doing so far, the last few classes, is really what's in every physics textbook under the you know, as the theory of what we're talking about is really the quantum theory of a particle in one space dimension. It turns out most of the tricky things that happen about in this theory, you first already see, even if there's only one space dimension. So going to 3 spatial dimensions doesn't change that much, but and we'll do that a little bit later. But so that's what we've been doing, and mostly I've been talking about a free particle. But what we did, but what we did last time when we talked about the position operator means that you can also talk about much more general problems of particles experiencing potential forces. So let's go again. Say what this theory is. So so the state space is well, it's I'm often being kind of vague about it. I explained the various kind of problems about various possibilities for state space. One was to think about just to think about the square interval functions, and this had some nice properties. And then, but sometimes we found to solve the kind of problems that occurred that this didn't give us what we wanted. We found that it was really a good idea to do 2 things. This was equal to its own dual as a vector space, or isomorphic, but we could pick some much more restricted thing, which was the which was the Schwartz functions, and we could take the dual of that, which was the temper distributions. So when I'm, there's always going to be some kind of vagueness when I'm talking about the subject, about which of these exactly I mean. But you should be able, from the description so far, depending on what you're trying to do, you should be able to pin down. You should be able to pin the problem down and work with, one of these choices, depending on exactly what you're trying to do. And then the main thing that was so now we had, so on the state space we really had two interesting operators. We had the momentum operator, which was basically just differentiation. So I'll leave h bar here for a minute. Q. Okay. And what this and so this guy actually has a kind of a significance, a symmetry significance that, and sometimes what I'll do is I'll call him the infinitesimal generator of space translations. Okay, and so this is kind of the more the physics terminology, which basically means it's the Lie algebra. It's the it's pi prime. Well, it's the Lie algebra representation of translations. So really, actually, what we have is we actually have a unitary representation of the translation group on our state space, which is just by translation of functions. And then if we kind of differentiate a translation at the identity, and then you get, and then we multiply by I. So let's say, really, what's happening here is, so here the space translations are psi goes to, well, anyway, so here, I don't know where to put this. This should really be what I mean here is psi goes to, no, let me do that. So, oh, no, let me just say this because I think it's just going to get confusing if I try to write this out. So, but you basically you're looking at psi goes to psi of q minus a. You're looking at the differential, the derivative of that at a is equal to 0, and that operator is minus ddq because I'm just by convention I'm differentiating them. I'm translating the minus term. I'm translating q to q minus a, and then I'm multiplying by an I to So the way to think of this is that really h bar is equal to, let's set h bar is equal to 1. This was just to keep the units for a minute, and then this is really minus ddq. So this is the skew adjoint operator of infinitesimal version of psi of q goes to psi of q minus a, and then I'm multiplying by an I in order to make it self-adjoint and use the physicist convention that we should be working not with skew adjoint operators but with self-adjoint operators. Okay, but then so this was the thing we've had for a while. But then what we talked about last time was q, which was just multiplication by q. And now, okay, and then so we introduced this new operator, and so we essentially have two different kinds, two quite different operators here operating in the state space. And what we can do now is we can take the so motivated by the kind of classical fact that you could take that if you're doing non-relativistic mechanics, what you do is you say that the energy is the kinetic energy plus potential and then that this is a half mv squared, or if you like, the momentum squared over 2m. So that's the standard kinetic energy, and the potential energy is just given by some function. Okay. So then, so what we do is we can take the Hamiltonian change this from a small p to a big P. I should do a better job of keeping track of this. So this is a small, this is the operator plus v of q, and q commutes with itself, so any function of q, it doesn't matter what order the q's are in. And then the Schrödinger equation becomes I h bar d dt psi is equal to the Hamiltonian operator, the Hamiltonian applied to psi, but the Hamiltonian p is just this guy squared. So this is minus I h bar squared over 2m plus v of q. Okay. And so this equation here is really kind of the basic equation that you'll see in pretty much any physics textbook that tries to talk about the, how the quantum particle. And it the case where there's no potential, where v of q is 0, that's actually translation invariant. That doesn't, if you put a v of q here, you're going to get something which changes if you shift q. So it's no longer translation invariant, and, unless the potential is a constant. But otherwise then you have a free particle. But in general, you have this guy, and so and this is a partial differential. I guess I should write this. Sorry. this should be a partial derivative. So this is a partial derivative in partial differential equation in two variables, t and q, and depending upon, and you'd like to actually solve this for various q's. Okay, so that's the, I think this is the typical physics. You know, we've now, I think, at least gotten in you know, through this roundabout method, through exploiting, trying to talk about symmetries, we've gotten to this, to a motivation for this equation. Now let's see. So what happens then in a physics class is you then typically spend a lot of time solving this thing. So we've already, you know, written down the solutions for v of q is equal to 0. That's just these so-called plane wave solutions. They're just these exponentials. But yeah, so let me just say a couple of words about that. And so physics class, as you start solving PDE for different v of q. Okay. And so, and for a typical example you start off with might be something like a potential well where the potential is 0, and then it's down here and here. For example, that this might be your v of q, and then, you know, this becomes a bit tricky because you have to worry about, you spend a lot of time worrying about boundary conditions. But anyway, this is a typical kind of example you do, and we'll do we'll later do v of q quadratic. And this is the harmonic oscillator. So towards the end of the class, we'll work on that problem and doing that from a different point of view, and we'll also talk about in 3 dimensions the inverse. The potential that's 1 over r, where r is the distance from the origin. So we'll talk about that. So we'll do this, but in all the cases where we're trying to do this, we won't so much approach it from the point of view of trying to solve a PDE, but we'll approach it from the point of view of trying to exploit the symmetries of the situation, and using representation theory to tell us what's going to happen. So that's that. Okay, but now okay. Okay, but now let me kind of summarize what I don't think I did very well last time, which is to try to explain that the role of the Fourier transform, and the fact that we actually have two. Well, actually, let me first, maybe a good way to say it is this, I guess, is that we have two. So given, since we have two very different operators, P and Q, what we can do is we can try and use the eigenfunctions of those operators as basis elements for our space. And so we have two bases for H. Okay. And one is eigenfunctions of P. And that's the things that are e to the I P over H bar Q, and very, very often what I'm going to do is I'll mostly try to set H bar is equal to 1, or I'll work with K, when I write K, I mean P over H bar, and if since I often want to just set my unit so that h bar is equal to 1, then k and p really are the same thing. And I'll often probably make the mistake of sometimes using k, sometimes using p, because they're really the same as long as my units are such that h bar is equal to 1. Okay, that's these guys. But you also have eigenfunctions of q. Right, and these things are the delta. Oh, and these will often, as a notation for these things, we'll often call these something like write these this way. And the eigenfunctions of q are things that are delta of q minus a. And we might write, well. And well, the notation, I guess, a little bit confused here, but let me, well, yeah. I guess I might just write, may write this depending on the notation. I write this as a, but this is a function that if you multiply by the q operator, you're going to get 0 unless except where q is equal to a, and there you're going to you're multiplying by q, which is a. So in some sense, this is clearly an eigenfunction with eigenvalue a. But the problem with both of these things is that so these are in S prime of r, not. Okay. So this is our main problem in this subject. That we want to use these things as a nice basis for our state space, but there's they're not actually in the version of space where you actually have a well-defined inner product. They're not really. I mean, this one certainly isn't a function in any sense. This one isn't a function in the L2 sense or anything. And so you have to think of them as distributions. Okay, but what you can do, but you can at least you can think of these. Can think of these as basis elements. Then you have a formula that the wave function psi of q, what it is, you could write it as the integral from minus infinity to infinity of delta of q minus q prime psi of q prime the q prime, and this is kind of true by definition of what the delta function is. And what this is, so what you're saying is you can actually think of an arbitrary function as kind of an infinite sum of delta functions, where the infinite sum becomes an integral, and the values of the function at each point are just the coefficients of the delta function. So you could kind of formally think of this as an expansion of this function in this basis. And you can do the same thing in the formula for the Fourier transform is then infinity to infinity 1 over square root of 2 pi e to the I kq. Or sorry. No, sorry, or no, sorry, I wanted to write it this way. It's equal e to the I q psi tilde of k dk. So the standard and this is just the formula for the Fourier transform. But you can interpret the formula for the Fourier transform as saying, let's, this is one set of basis elements labeled by Q prime. Here's another set of basis elements labeled by K. And so in some sense, the normalized basis elements you want to use here you'd want to put a square root of Q prime there maybe. And you can think of the Fourier transform as the coefficients when you expand this function in this basis. Anyway, so it's another way of thinking what we've done by having these two different operators is that we've given ourselves two different bases of the same space to work with. Okay, and now the Fourier transform formula is really then just is just exactly the formula that tells you how to get from the coefficients in this basis, which are the psi of q's, the coefficients in this basis, which are the psi tilde of k's. And it's just the second formula here is just the is just the change of basis formula. Okay, so I'm just going to say this. So I wanted to say that the so the Fourier transform so you can think of this as being F, call it F, and so remember, so this thing has the nice property that it takes Schwartz functions to Schwartz functions, L2 functions to L2 functions, distributions to distributions, but it and in each of those cases, the Fourier transform is a unitary change of basis. Basis operator. If you like, you're going from the delta functions in Q to the delta functions in P, and vice versa. And the Fourier transform formula is the change of basis formula. Okay, and yeah. Okay. So now in the So we'll often want to work in the basis, basis of momentum eigenstates. And then these are described by so a vector is given by So by this other function. So there's going to be two functions. We're going to have psi of q, which so you can think of these states as given by wave functions of position, depend upon where you are, or you can change basis and think of a state as given by the Fourier transform, which is a function on the k space, or if you like, in the momentum space. And on such functions, and so you can check if you work with these guys instead of the psi of q, you can check that then the operator p, the momentum operator, is now just the multiplication operator. And so I've been calling, again, I'll identify P and K. So P is just multiplication by K. And then you can check and see what the Q operator is, in terms of the Fourier transform. And remember, and then when you in the Fourier transform, under Fourier transform, multiplication and differentiation get interchanged. And so I think what happens in Q, the Q operator becomes I H bar d dk. Well, again, let me get rid of the I. I think I have to check this, but I think you pick up a different sign here. You have to check that. Okay, so you can. I mean, the way to do calculations in the subject is to think of yourself as that depending upon your problem, there's two different bases you can work with. You can work with the Q basis, or you can work with the K basis. And what you would actually like to do in some case, and this is what the Dirac notation. So let me say that one thing about the Dirac notation is that it tries to write things down in a basis independent way. It tries to so in the Dirac notation you can have psi so you write elements of your state space this way, but this notation is meant to be to be independent of which basis you choose. This just means you've got some element of the state space of this complex valued vector space psi, and if you so this is like saying that V is element of a vector space, but not actually giving the coordinates of V at any particular basis. But the psi of Q or psi tilde of K, are the coefficients in a basis. So one thing that I'm often doing when I'm using this Dirac notation is just trying to think in a basis independent way, that it doesn't, I may want to do some calculation and not have made a choice of which basis I'm in. And then the so elements, things like psi, if you write them on the other side, you should think of what you're doing is you're taking the you're looking at the dual space, although you're also putting in you're looking at the conjugate dual space, and so this is element of H star, and I guess you should think of there being a conjugation going on there, and this is given by things like you can write these in the Q basis or in the K basis as some psi of Q bar Q Q, or and these intervals are off minus infinity to infinity. My tilde bar K. So you should think of, if you see these things, these are meant to be more elements of this conjugate dual space. So these are things that if you feed them, then these are things that you can feed these guys and get numbers, and then the number that you get is going to be the psi 1, psi 2 is going to be well, anyway, it's going to be the integral. Actually, let me write it this way. It's just the usual inner product. Okay. Okay, so one aspect of what I'm going to do with the Dirac notation is this, and if I'm putting in some kind of label, something that's clearly labeling a state like psi, then this is what you should be thinking about it. You should be thinking that what I'm trying to do is I'm just trying to write down one of the abstract vector in this space corresponding, to one of these things depending upon your basis. And if I write it over here, I'm trying to think of it in the dual. Now where this gets confusing is okay. So this makes perfect sense as long as I'm talking about something that's in L2 or something that's in the Schwartz space, so that all of these things make perfect sense. The problem is that it's often very, very convenient to extend the Dirac notation and to start talking about things that are actually distributions. So we extend this notation to include distributions. And so then the typical thing is what you want to do is you want to say, so the kind of formula that you want to write is this, that delta, that the Q. So this is the integral delta Q prime minus Q. So what we want to do is we often want to one way of using these kind of non-normalizable states like this, these distributions, is to put them in something like this, where here you're going to have, as long as you have if you have a Schwartz function here, then so this is a linear functional, but it's a linear functional. It's not going to make, for it to make sense, you have to put a Schwartz function here, and then you're going to get the actual coefficient, the actual function as a function of Q. I think maybe I better not try and say more about this, but anyway, so you can make sense of like Q, P, and so for instance, to make sense of this guy, you would take the expression for this guy as a function of Q and put him in there. I won't try and do this, or things like Q, P, etc. And what there are really kind of two ways of thinking about what you're doing when you're working with a notation like this. Or I might want to take integral of dq. And there are two ways of making sense of this guy. One is really kind of, assume, make H finite with cutoffs. So you make this thing periodic, and then you put in a momentum cutoff, and so that the space is finite. And then these formulas, these become then the integral goes to sum. All integrals become sums, and these formulas are all just these are all just formulas from linear algebra about what about the relationship between various basis elements. So you get linear algebra. Or relations between basis elements, or the other thing you can do is to give the find a correct interpretation as distributions. So the formula makes sense. If you feed it certain Schwartz functions. Okay, so anyway, so this is really just kind of meant as kind of an explanation of what you should do when faced with some of the standard kind of calculations that you'll see that I may do at various points that you'll see in the physics books, which are which use this Dirac Braun-Kett notation. And if you're things it's pretty much a standard story about a vector space and its dual, as long as you're dealing with Schwartz functions or L2 functions. It's when you're dealing with these guys, it's you have to kind of try and interpret what's going on in one of these two ways. To just kind of say that, well, people are what's happening is that we're pretending that this infinite dimensional function space is really finite, and then we're just trying to do linear algebra on it. Or you can say that we're doing our formulas are not formulas about functions or about element. They're formulas about distributions, and you have to kind of look at the formula and figure out, what is this thing? This is something that if you feed it Schwartz functions in a certain way, it's going to make sense. You have to figure that out. Okay. Okay, so maybe it's a good point. So are there any questions about this? So this is really meant as just kind of an explanation of what's the fairly standard story that you'll hear, that you see in any physics textbook, or if you've seen in quantum mechanics you might have seen before. But are there any questions about this story at this point? I haven't. Anyway, it's about all I want, because I want to stop talking about this and move on to something else. No, you sure this? Okay, so we'll drop this for now, and you just have to. You may need to come back to this and to try to make sense of some things I'm saying later. But so what I want to do today is talk about a new idea, which is that is that to realize that what we've done is we've talked about two different these P and Q operators are generators of two different, acting on the same state space. They're generators of two different, two different groups R. Let's see. So we have to notice. So let's just say this. So notice. So we have. So let me just say it this way. So H is a unitary representation let's call R of R plus R. So really what we've done is we've and so this guy is just the let's write this guy. This guy is the translations. Okay, so we can just take our, since if we have a representation as functions, we can just move it, translate it back and forth. But this other guy is, what is it? So this is the guy. So this is generated by P. By P. So P is the infinitesimal version of this guy. If you exponentiate the differentiation, that corresponds to a finite translation. Well, here we've got a different guy. This is infinitesimally. This is multiplication by Q. But if you ask, okay, well, if this, what happens if you exponentiate the action of multiplication by Q? Well, again, and again, there's a factor of I in order to make this. So in order to make this skew adjoint, we put in a factor of minus I, and then we exponentiate. So you get a group. Psi of Q goes to, well, psi of Q, instead of just multiplying by Q, you multiply by, you exponentiate with the factor of A, and you put in a, I wanted the, minus I, and you put in a minus I, so imagine that it's this guy. Okay. So, or you could thought of it from the other direction. I could have told you, okay, look, we're going to what we're going to do is we're just going to get an action of the group R on functions, and the action is corresponding to a element of R. You multiply by e to the minus I q a times your function. So this is just this is a unitary representation of R on these functions. And if you differentiate it, if you differentiate with respect to a at a is equal to 0 and multiply by I, you just get multiplication by q. Okay. So we have these two things. Okay. And now now the problem is that we'd like to say, but this is not. So this is not. It's not. Sorry. Okay. Yeah. Okay. Yeah. So I don't actually have the problem. Problem is maybe I better just say it like this. So we want. We know that it's a unitary representation of this guy, and we know that it's a unitary representation of this guy. But the problem is, for it to be a unitary representation of both, then it has to. This is a commutative group, and so it shouldn't matter in which order you do these. So the problem is that Q P is equal to I H bar times 1 is not equal to 0. So we don't get representation of R plus R. Because, anyway, but because the problem is that, I mean, this is a commutative group. This guy, the Lie brackets in here are all 0, but then but if you take the Lie bracket of the generator in here and a generator in here, you get something which is non-zero. Okay, so this is not if you take this group, this nice commutative group, and you think of think of it as acting as a representation of these guys by doing these things separately, you have a problem that this is a commutative group, but it turns out it actually matters which order you do these in. If you can check that if you do this and you do this, then do this, you're going to get something different than if you do this, and then do that. The order of these operations matters, and infinitesimally that means the commutator is non-zero. Okay, so that's the so what we're going to do is to so the idea. So now I want to head off in a bit of a direction which is more of a mathematician's direction about how to handle the situation. I think the typical physicist reaction to this is that, well, so what? This just means that it's actually not a great idea to try to think of this as okay, it's not a representation of this, so what? But what we'd like to do is we'd like to extend R plus R to a three-dimensional the either algebra or group, and get a representation. Okay. So what we're going to do basically is say, okay, well, we can solve this anyway. So let me just get to that and start saying that. But this is what we're going to do. We're going to try to make this H actually be a unitary representation of a Lie group, which is not this guy, but something that's got one extra dimension, one extra component. Okay, and the terminology for this is a little bit funny. So this is going to be.
Professor?
Yeah.
What's the physical meaning of this extra dimension? Can we associate a physical quantity to that?
Anyway, we'll talk about it a lot. We'll say a lot more about it. But it really is a yeah. I mean, it isn't so. I think it's actually fairly mysterious, but it actually goes back to well, I think wait and see. I mean, we're going to be talking about it a lot, but it's not something that you normally, that's part of your normal physical picture of what's going on. It really, but if you I think the thing to say, and what we'll see today and starting next class, is that if you're used to thinking in phase space, that it's a very natural. It kind of appears. It's kind of a natural aspect of phase space also, but it's not. Yeah, I mean, maybe one way of saying it, maybe to try to give it a little bit of an interpretation, is that you should say, well, your wave functions are complex valued functions, and so you can always multiply them by a phase. And so it's that so this is not quite anyway so there, well, maybe that's about as good as I can do. I think is to say that that the at the Lie algebra level it's going to just be given by that by I times that identity operator. If you exponentiate that, that's just a phase, an overall phase. So in some sense this is kind of telling you about that you also have to keep track of the phase information in these functions as a piece of the symmetry. I don't know if that really helps, but anyway, let's see as we go along. But it's not. I'm not telling. This isn't. Yeah, I mean this doesn't have kind of a kind of a physical interpretation you would normally of the sort you'd normally be looking for.
When you say phase, like, do you mean like the phase that's generated by like time translation, or is it another phase?
Maybe let me. But basically, well, just let me just say one thing before actually really trying to do this right. But basically, remember what I'm saying is that the problem is that you've got an operator Q, which generates one direction, and you've got an operator P, which generates another direction. And the problem is that they don't commute, and but the lack of commuting is given by the identity operator times an I, and then an H bar is equal to 1. Okay, so you should think of the kind of extra. If you think of it, this is generating a certain symmetry. This is generating a certain symmetry of translation. This is generating a certain symmetry of multiplying by a Q-dependent phase. Well, what this guy is doing, he's just the identity operator times I. If you exponentiate him, you just get e to the I, a or something. So so the exponentiated version of this operator is just a phase transformation. Here, this is something much trickier. This is if you exponentiate this guy, you get an e to the I q a. You get it's a phase, but it depends on q. So if I try to say, okay, what's the new operator that's been thrown into the mix is real, and if I want to think of that as generating a symmetry, it's just it's really just the identity operator times I. So if I exponentiate the identity operator times I, I'm just getting a phase. So that's what I mean. Does that help?
Yeah, I guess it would be much better when we see it systematically.
Yeah, but we'll, as we go along, it's but it really is kind of a fun. Anyway, anyway, yeah, there are a lot of different ways of thinking about what this extra piece is, but they're not none of them have any kind of classical interpretation. This is very much a quantum thing. Okay, so let me go back to the what we want to do. Okay, and so let me start the way a mathematician. Let me start at this direction a mathematician would take. And so the funny thing is that this Lie algebra, this Lie group. So really, what happened historically was that Heisenberg found these commutation relations, and and showed them to a bunch of people. People who saw this, one including this mathematician Hermann Weyl, and so and Weyl immediately said, "Wait a minute, that looks like your commutation relations of these operators look like exactly what I would expect from a if there were if this was a Lie algebra representation of some group or of some Lie algebra." And so the Lie group or Lie algebra that we're going to be talking about, physicists will often call it the Weyl group, but mathematicians call something else the Weyl group. So mathematicians always call this the Heisenberg Lie algebra and the Heisenberg Lie group. Not because Heisenberg even had any idea what a Lie algebra was or what a group was, but because they come from the Heisenberg relations, and we don't want to put a Weyl's name on it because we're already using that for something else. So, but let me just define it. So what I'll do is I'm going to start with the Lie algebra, motivated by that relation. So what we're going to do is I'm going to define the Heisenberg Lie algebra. And then I'm going to use exponentiation to get the group. And the definition is going to be so what this is the Lie algebra algebra with the vector space R3, so it's 3 dimensions, and then with brackets on a basis x, y, and z. Okay, so what we're going to do is we're going to write this Lie algebra in kind of a formal way, in the sense that what it is it's going to be as a vector space. It's R3, but I got to put a bracket relation on vectors on here. I got to put some kind of bracket relation, and I'm going to write the bracket relation in terms of a choice of basis elements x, y, and z. So there's some choice of basis elements such that the bracket that x, y, so the bracket of these two is this guy, and then this guy commutes with everything. So you have xz is equal to yz 0. Okay, so it's got kind of one direction that the bracket in that direction with any other vectors gives you so you should think of it as being, there's one direction which is the z direction, and then there's just 2 directions which are the x and y, and that if you take the bracket of 2 things in here, you're going to get something going out in the z direction. But if you take the bracket of z with any of those, you get 0. So z is kind of a commutative direction, and x and y are kind of a non-commutative directions. So that's but this actually isn't. And so sometimes I'll write this as R2 plus. So I'll write it as I'll break out this direction where the z is going to be, and the other two, and with elements. So I'll write x, y, and z. Okay. So these are small x, y. Okay, so I want to think of elements of this R3 as elements of an R2 direct sum with an R, and the coordinates over here will be x and y, and the coordinates here will be small z, and big x, y, and big z are the basis elements.
So is it the algebra of the Lie group x2 times x1? No. It's a new Lie group, and the okay. So one thing you can do is you can identify with the matrix, the algebra. So what I mean by matrix Lie algebra is a Lie algebra where the bracket operation is the commutator of matrices. Okay, and so what you do is you just take x. Let's just say x is equal to I gotta put it here 0, 1, 1, 0, 0, 0, 0, 0. Y is equal to 0, 0, 0, 0, 0, 0. 0, 0, 1, 0, and z is equal to 0, 0, 1. Okay. So I could take one way to realize these relations is to take these matrices, and if you compute this, you'll see that the commutator of this guy and this guy is this guy. The commutator of either of these guys with this guy is 0. Or another way of saying this is that it's This is the Lie algebra of matrices of strictly upper triangular or 3x3 matrices. So, in this x corresponding to x, y, and z, we're gonna, as a matrix, we're gonna write it this way: 0, x, z, y, 0, 0. And now these are supposed to be small x, small z, small y. Sorry. Okay. So this is a Lie algebra of matrix given by matrices, where the Lie bracket is matrix commutation, and this is it. And so from a mathematician's point of view, this is actually a very, very natural Lie algebra that comes up in a lot of different contexts. Have nothing to do with quantum mechanics. Because if you have just the fact that if you have two upper triangular matrices and you take the commutator of them, you start pushing elements, get pushed off in this direction. And so you take the commutator of two things in this form, you get something up here. And if you take more commutators, you get 0. Okay, and so the and I won't write this out, but you can do the same. You can do the same thing. Anyway, yeah, you can do the same thing in higher dimensions. You can take D. You can make these guys vectors, and then put a vector here, and a scalar here, and you get a higher dimensional version of this. But anyway, what I wanted to do then, the reason for starting with this guy was to then I wanted to find the Heisenberg group is the group that you get by exponentiating this Lie algebra. So let's get this definition. The Heisenberg group is the group you get. Let me say that you get by exponentiating these matrices. Such matrices. Okay. So it's a standard. So then you make the definition of, you make this thing a Lie algebra corresponding to Lie group by saying, the group is exactly the thing you get by exponentiating these guys. Okay, and then what you find, so you find that if you exponentiate these matrices, let's write this way: xp of xz 0, 0, y 0, 0. What you get is if you work this out, you'll get one. You get stuff that's still upper triangular with ones on the diagonal, and you get x here. You just get x here. You just get y, and then here you get x plus a half x. Well, that's right. Z plus a half xy. Okay, and so we're going to so what a mathematician will often say is that these guys, I've written, so this is just the group. So and let me call this H. I'm going to often refer to this as H3. So the Heisenberg, it's H for Heisenberg, and 3 for the fact that it's got 3 dimensions, this x, y, and z. So often what you say is that H3 is the group, is just the group of matrices of the form 1, 1, 1. Sorry, okay. Matrices So another way I could have gotten to this is to just said, okay, look, I'm going to tell you about a new Lie group today. And the new Lie group today is the group of all kind of upper triangular things of this form. That it's identities along the diagonal, and that anything here, and anything here. Okay. And so what we'll do, anyway, but then if you want to kind of take the logarithm and figure out, so if you want to figure out, what is the thing that gets exponentiated to give this? Well, A is going to be X, C is going to be Y, and then you have to then figure out, and then Z is going to be, anyway, Z is going to be B minus a half XY or something like that. So there's a little bit of a funniness going on there. And now what I want to do, yeah. You have a question?
Is it true that for this exponential map from the Lie algebra to the Lie group, it's surjective?
Yeah, and even better. So this is a map. So as a, yeah. So let me actually say this. This is what I wanted to say. So as a space, H3 is just R3, if you like. And then, so then EXP such that Lie H3 goes to, so this is R3. This is taking R3 to another R3. And this is actually a one-to-one map. This is actually a nice diffeomorphism. And so we can think of this. So this is one-to-one C infinity, and it's so you can think of this as providing global coordinates on so you can think of, so you can take X, Y, Z, the element here, as global coordinates on H3, instead of this ABC business. Anyway, so this exponential map is a so the situation is actually just very much like in the additive group. When you're talking about the additive group, the exponential map, again, is a diffeomorphism between the Lie algebra, which is of the real numbers, and the Lie group of the real numbers with the with addition. Well, it's the same thing here. So what we're often going to do is we're often going to we're going to use the same. This is sometimes we can use this to mean an element of Lie algebra, or we can also use it as coordinates on the Lie group, as also as an element of the Lie group, and we just have to say which one we're talking about. Okay, starting to let me then quickly get to what I want to the kind of punchline of what I want to say today, and I guess I'll better pick this up the next time. Okay, so let me just tell you the punchline to all of this. So the main theorem. So up to up to a unitary change of coordinates. There is a unique unitary representation commutation of H3. And it's the, such, let me say it this way. So for each, so there's a unique rotation of H3 for each, let's call it some number C for each real number. And it's given by H is just our functions. I guess we better take this to be H is L2 of R if we want this to be this to be a unitary representation. So H is just functions on R, and then and we'll take it. And what I'm going to call, and I'm going to call this. I'm going to give this a name for various reasons. I decided no longer to call this a pi, but a gamma, and this we'll call it gamma S, and it's called the Schrodinger. It's called the Schrodinger representation. And what happens, which satisfies gamma of S. So the corresponding Heisenberg thing. Let me say of gamma S prime. So on X, you get minus I Q psi of Q gamma S prime of Y Q is equal to a minus I P and then gamma S prime of Z is equal to minus I guess I should minus IC psi of Q. Okay, so let me just say, so I'll pick this up next time here, but the idea of this point of view is that this now realizes what I was trying to get at before. I was saying that it looked like we seem to have a two-dimensional Lie algebra that was acting on our state space in an interesting way, but there was a non-trivial commutator, and so you can think of this X as generating generating one of the R's, one direction in H3, and it's just this multiplication by e to the IQ multiplication by minus IQ infinitesimally, or if you like, when you exponentiate this, you're going to multiply by a phase, e to the IQA. And then the other direction is given just by translations on functions. And then the guy who's a commutator of this guy is going to act by a it's going to be act by something, and if you exponentiate, it's going to just be that phase. So what we've done here is we've shown that you can solve the problem of turning this whole story about a one-dimensional particle, and you can turn it into a story where the state space is a single. It is. Sorry, there's a unique irreducible. So, I mean, the funny thing, the thing about what we were doing before, we were looking at groups R acting, but they were highly reducible. They were acting on an infinite dimensional space, and they had
lots and lots of this infinite number of kind of one-dimensional, irreducible subrepresentations. Well, the point is that it's in some sense one way of characterizing what the quantum mechanical state space of a single particle is that it's exactly given by it's exactly an irreducible representation of this bigger group. This group, which is the two kinds of translations that we knew about, put together with a kind of a third, more trivial kind, which just gives us this phase multiplication. And so something very funny is going on here, and I'll say more about it next time. But what's going on? Notice that this group here is kind of very peculiar in the sense that they're every other group that we've run into before had lots and lots of unitary representations, like the U1 had these unitary representations labeled by an integer. SU2, they were labeled by a natural number. Here, there's only one of them. There's really only one. There's only one irreducible representation of this guy, and he's in some sense the thing that I spent the last couple lectures telling you about in the guise of a free particle. He's exactly this is exactly the state space of a free particle, and the information that you need to get the representation at the Lie algebra level is just the Q operator, the P operator, and then just scalar multiplication by and then just scalar multiplication. And so one reason you often don't hear this story told this way from the from the physics point of view is that you can't, there is only one representation, and this is anyway, so it's a very peculiar story. There's all of the stuff which you do about Q and P operators is kind of built into this one representation, but it's a single representation. So the classification theory of representations of this group is very funny. There's really just one. If you okay, so anyway, maybe I better stop there now and stop now. We'll talk more about this next time. But are there any questions about this right now, or if you want to talk longer, we can come back. But any questions about this or the stuff that led up to this so far?
Yeah. So just to make sure, so gamma of S maps from like H to some unitary group. I guess it's dimension theory that you do.
No. Yeah. So yeah, actually yes. It's this one by a bit fast, but the gamma of S. Yeah. So gamma S is the Schrödinger representation is something that takes G. It takes G. Well, so what you've got is you've got group elements in H3. In H3. These are these 3 by 3 upper triangular matrices, right? Goes to the representation gives you. Remember what a representation is you're going to get a unit. You're going to get a unitary operation. This is a unitary operator. On L2 of R. Okay. So this is definitely not a matrix at all. So there are, there was the matrix representation of this guy that you were given the defining representation of this. So the defining rep of H3 on C3, if you like, is not unitary. Okay. So we were given a representation of H3, just the definition as matrices, right? And that acts on C3, but that's not a unitary representation. So this one we're not interested in.
what's interesting is that it has an infinite dimensional representation. So this is a representation that you really can't think of in terms of matrices. You have to think of it really in terms of multiplication and differentiation operators on functions. And it's this guy. And what I did is I wrote down, I didn't write. And actually, in the notes, I kind of work out what the a formula for these guys is. But I didn't write a formula for gamma of S. I wrote formulas for the Lie algebra representation, so on a basis of LHC. That was the XYZ. Okay. Does that help at all? So it's this is a very sophisticated piece of representation theory, because this is representation theory acting on infinite dimensional irreducible representations. So this is something that you actually haven't seen before. Every infinite dimensional representation you've seen before on functions was highly reducible. It could be broken up into into smaller pieces, and into one-dimensional pieces or pieces of a certain spin. This is an infinite dimensional representation which is irreducible. There's no way. This has no sub-representations. Okay.
Yeah, that helps clarify a lot. Thanks.
Anything else about this? Okay. Well, anyway, if you have more questions, come back in a minute on the other Zoom session. And I'll pick this up here. I think what I'm not going to do. I wrote out in this chapter 13. I wrote these formulas out in kind of painful detail for working out exactly what these guys are. But so you should look through that, and I think those calculations should make sense. I'm probably not going to go over those again next time, because they're not especially informative to kind of work out. But the bottom line of this representation is he's really just he's a very, very non-trivial, irreducible, infinite dimensional representation of but whose Lie algebra version is exactly the whole long song and dance about the particle in one dimension that you heard about, and so you have to kind of rely on everything you've learned about that situation of physics to kind of understand what this guy is, and physicists pretty much always think about this at the level of Lie algebra representation. That's where the operators are that you are used to, that you need. They normally don't think about these guys, and they normally don't think about this group. And as I said, often when physicists do think about this group, they'll often refer to it as the Weil group. And sometimes they'll also talk about the homomorphism property of these operators as being the exponentiated Weil version of the commutation relations, or something like that. Okay, maybe that's it for now, and come back in a minute if you want to talk some more about this. Okay. Hey, bye for now.
Thank you.